to have Dawid Kielak going to tell us about firstly free-by-cyclic.
All right, thank you very much. Thank you for coming. Thank you for having me. Okay, so I'm going to open like every good TED talk with a question, and the question is, and it's really the whole talk is just propaganda for this question. Okay, the question is, why should we study free-by-cyclic proofs? Okay, so this question has two answers. One answer is, I think, very applicable in this audience. I hope it's going to resonate with you. And the answer is that free-by-cyclic groups, or virtually free-by-cyclic groups, are the right analogs of virtually fiber tree manifolds. Okay, so if you are sitting here and you already have proven all that you wanted to know about virtually fiber tree manifold, now here's a new class of groups. You take your tools, you move to a new sandbox, and you try to build a new sandcastle dock. Okay, so that's one reason. Why should you really do it? So it's not just because we are bored and you have nothing better to do with our time. The point is that many theorems which call for fiber tree manifolds really have analogs. So that's a nice thing. And sometimes the proofs are not the same. And that's a good thing, okay? Because when you have to move to a new setup and you know where you're going, but you have to use new tools, you are learning something new, right? And then you can take the tools back to your free manifolds and maybe you have learned something about free manifolds again. Maybe you have a new proof of your favorite theorem. But also sometimes when we do this and we find this new proof, and we prove technically new is true anyway, free-by-cyclic groups, we actually figure out that our proof works in the edge greater generality. Okay, it turns out that it's applicable to some possibly bigger class of low-dimensional groups. And that brings me to the second answer to my question: why should we study free-by-cyclic groups? Because it turns out, and I'm going to try to convince you of this in this talk, that lots and lots and lots of low-dimensional groups are virtually free-by-cyclic. Okay, more than we suspected. Okay. Yeah, so they're worthy of study because they're actually pretty better. They're much more common than Okay, right. So let me start with the definition, so we avoid any confusion about what I mean. So G is free-by-cyclic. It's all joined with Marco Linton. So I have to do it. And otherwise I forget. Good. So G is free-by-cyclic. Okay, that's the definition. If and only if G has a normal free subgroup F and the quotient is cyclic. Okay, so I hope there's no confusion from now on. When I say free-by-cyclic, I do not mean that the normal free group is finitely generated. I don't mean that. Sometimes I will, and I would stress it, but in general I don't. Also, I don't insist on the cyclic group being Z, though in practice it will always be Z. Okay, but the statement should be true even when it is not Z. Yeah. So by free-by-cyclic, I mean this is free-by-cyclic. No more than that. Yeah. Of course, the closest analogs to free manifolds are the free-by-cyclic groups where the 3-bit is finitely generated, but that is a bit much to expect for reasons of Euler characteristic. I will get to that later. Okay, so now we know what we are dealing with. So just to stress again, the free group is not necessarily finitely generated. And now let me write a kind of a.
Is that comment about Euler characteristic?
Is the what? Sorry.
Repeat the comment. It's too much to expect as well.
Yeah. So free-by-cyclic groups, free-by-Z groups have the Euler characteristic dependence of the free if the kernel is finitely generated or not. That was observed by Jack Barton.
So you're insisting that the free groups be finitely generated?
No, I'm not. I'm saying that Euler characteristic 0 forces that, and Euler characteristic non-zero forces the non-finite generation.
So why aren't the non-finitely generated free-by-cyclic groups analogs of the Euler characteristic negative free manifold?
Yeah, I guess that's idea. Right. Yeah, thank you for the comment. Okay, let's move on. Theorem. So this is going to be kind of an aggregate theorem, and I'm going to do the one thing one is not allowed to do in the talk, namely I will not introduce the theorem to people. I'm sorry. Okay, if you are behind one of these theorems, then I sincerely apologize. Okay, so let G be a finitely generated, the group is finitely generated, okay, and free-by-cyclic. I don't mean the free group is. What do we know? So we know lots of things about free-by-cyclic groups. And we know that the homological dimension, I will do it over Q because maybe I want first free-by-cyclic. And the homological dimension over Q is at most 2. That's not hard to prove, but that's important. What else do we have? We have residual finiteness. Though again, I don't really know if it's about it. Really finite. We have coherence. So this is Pendel. What else do we have? Well, we have a bunch of these nice conjectures. We have the Farah-Jones conjecture, for example. Jones. This actually, I do know who proved it because it was Charlie, Benjamin Brook, and myself. There's the Baumgarten conjecture. And that one proves using standard script of Baumgarten. I don't know how all they are, but they should go to the very beginning.
Do you remember
Sorry?
those things say?
No. So these are right. So these are conjectures about K-theory, various K-theories, and why they are the same. Okay, and they're from the same conjectures. I don't want to go into it. The point is that why are these things important? Well, either you are an aficionado of K-theory and you just like it, or they give you also the standard conjectures, not the concurrent conjecture, follow the course. Okay, so this is what people. Okay, whatever, doesn't matter. If you don't care about them, you don't have to start caring now. It's not important. There's one thing that you probably don't care about, but I do, so I will still say it. It's the Atelier conjecture. So that was proven by Linel. And the Atelier conjecture, I will not say what it says, but it will be useful later on. Actually, no, I will, sir, because that is in the audience. So why is the Atelier conjecture so important? Because it gives you the most important thing of all things. It allows you to embed the group ring of G into a skew. Okay. So it's extremely important. By far, the most important. Okay, there are some open questions about free-by-cyclic groups. It's still open when they're linear. Okay, we have no linearity. Okay, sorry, my notes are floating. Don't do that. Right, there's another thing. Right, we don't know how to solve the isomorphism problem. It's a very closely related to confidence problem. Well, the third isomorphism problem. We don't know. What else don't we know? But this is not going to be an exhaustive list. Okay, it's just some things that came to my mind yesterday. So we know from well, there's a theorem of Brinkman and then a model of version by Mutangua. We know when free-by-cyclic groups are finitely generated free-by-cyclic groups when they are hyperbolic. So take here, so G is hyperbolic. It can only it does not contain the squared. And so we understand that when these groups are hyperbolic. Now the question is, which subgroups are quasi convex? This is a very cool question.
Dawid, I think there's a question. For Linton group, do you also need to assume no quantified groups more than?
I don't think so. I thought so. Mutangua's the result is about said that you cannot have concept solitas, but he deals with finitely generated ascending agents and extensions of finitely generated free groups. That's a slightly different setup. My groups are all a subset of his groups, but for a big free by set group, you don't get concept solitas.
You might think DS1 too, is it an agent sentence?
Yeah, but it's not free by set. That's the point. The kernel, because the kernel is not free. You must have that the kernel is not free. Yeah, that's exactly the point. Yeah. Yeah, thanks. That's a good question. So which subgroups are positive there? We don't know. We would like to know. Okay, cool question. And there's one more.
We know someone with finite height. We still know how to prove it.
Okay. Right. Okay, and there's not one more question to ask. Because of Martin's talk yesterday, so finite rigidity, the question would be: can you generalize new theorem? Can you show that within the family of free-by-cyclic groups there is at least a finite one finite rigidity, and we know that by a result of Kudzinska and Hughes. We know it for the free-by-cyclic groups which have organization of rank 1. Okay, which is the generic case, but still nice to know it in full. Okay, so here are some of the problems. Here are things we do know.
Do we have good boundary theory for those?
Good what, sorry?
Do we have an understanding of some boundary?
Study for the hyperbolic.
No, in general, complete like.
No, I wouldn't say. Okay.
When you say free-by-cyclic, you mean finitely generated? Not the pieces, but more.
Yeah, typically I do like in this here. Yeah. Right. I mean, otherwise they're not necessarily really finite. So I mean, for most of these questions, I probably just mean finitely generated free by Z. Okay. Okay. Good. So this is where we are. Now, the new stuff. So, what I really want to talk about now is how to recognize a partially free-by-cyclic group that went into hiding. Okay, so if we will follow Martin's general philosophy of life, you pick random groups from the gutter. That's what Martin does all day, apparently. And maybe it is a partially free-by-cyclic group, and how can you tell? Okay, how to tell if a group is virtually free-by-cyclic. So it is not easy to tell, but there is a theorem that I want to advertise. So first, there's a conjecture. So as an example of this sort of question, here's a conjecture by Baumslag from 1986. And Baumslag looks at one-related groups with torsion. So the conjecture was that all one-related groups with torsion are virtually free-by-cyclic. Okay, just to remind you what are one-related groups with torsion, you take a bunch of generators, n generator, you throw in a relation, and you raise it to some power, and the power is 101. That's about exactly what one-related groups with torsion are. Yeah, so you write a group like this, and then can you see immediately that such a group is virtually free-by-cyclic? No, you can't. But I suppose Baumslag experimented, and he could prove in many cases that it is. So he answers conjecture. I don't think he really believed in it, and my feeling stems from the fact that he wrote a paper about the potential counterexample. But yeah, the potential counterexample ended up not being a counterexample because this actually is true. Let me explain why. So here's the main theorem. Myself and Linton. So let G be a hyperbolic, vertically compact spectral group. Okay. Yeah, and now here's the statement. G is virtually free-by-cyclic. If and only if, two things happen. First of all, you need the cohomological dimension of G to be low, but certainly without that, you have no chance of being free-by-cyclic. So what's the second thing? You want the second L2 Betty number of G to be 0. Okay, so that's the second. I will talk about L2 Betty numbers in a bit more detail later on. For now, we just think of it as a black box, that's an invariant. Okay, it's a number group. So this is a complete characterization. So if you care about hyperbolic vertically compact spectral groups, and if you care about groups of low homological dimensions, then it completely answers the question which ones are free-by-cyclic, which ones not. Yeah. And it turns out, as you can see, that I mean, this is not a very restricted thing. There's nothing. Good. So now, what I want to do, I want to very briefly tell you how this theorem implies this conjecture, and then I'm going to bore you to death with details of the theorem.
Why do you say virtually compact special? I mean, virtually special implies.
What does that imply?
I mean, if it's hyperbolic, then if it's virtually special, then it will be virtually compact. That's what
Unknown.
no.
Well, the master says unknown.
You're hyperbolic and you're totally finishing the race to me. If you're hyperbolic and you happen to be a subgroup of a rad, please everybody go and figure out that you're compact, that you're virtually compact, so that you're compact with you and
Wait, but you're
no, you're not just co-compact with you, you're doing it. Okay.
then that's in your book.
Grace.
Yeah. Well, they should one
Carry on. Sorry, okay, you're all satisfied?
So when you say free-by-cyclic, you allow them free the input.
Yes.
So what's wrong with the
Wrong with the second group? It's nothing wrong with the second group. It is free-by-cyclic.
for example, the back number?
Second is the second. So that's a 2.
There are other numbers which prove that this is by
All those.
over.
I would say.
Oh, okay.
Okay, so how does, sorry. So how does the theorem apply to conjectures? That is what I want to explain. So it starts with the theorem of Newman. This is the spelling theorem. There's a wonderful paper on the archive about Newman and his life history. So I encourage you to read it. It's very interesting. So this is 68, I think. So when other people had better things to do in 1968, Newman was proving theorems, and he proved that one related groups often are hyperbolic. He didn't use the word, but proof. So that's human. Then we have more recent result. This is, you can get this one right. This is Weiss 2021. And what the Dani showed, they are also directly compact-special. So that's good news. And what else do we need to apply the theorem? Well, we need the cosmological dimension and we need the Betti numbers. That is standard. So I think it's maybe due to Linden. In ancient mathematics, cosmological dimension is equal to 2. And finally, there is a paper of Dix and Linnell where they compute two Betti numbers of one related groups, and in this case, the second two Betti number. Okay. So this is a maths and facts. 60 years of mathematics, you can start from Linden to more than 100 years of mathematics, and that's the only case. Yeah.
All the stars are doing things.
Sorry?
All the stars are coming back.
Yes, that's right. Exactly. So that's it. So this is how abstract conjecture follows from the theorem. And now I will deliver on my promise, and I will bore you with the details of the main theorem. So let's do that. Okay, so now I really want to spend the rest of the talk proving the theorem. So prove the main theorem, and I'm going to do it in 2 goes. So first, I want to look at special case. And the special case is important, and it kind of shows really what's going on. And then I will comment on the general case. So the special case, it will seem a bit unmotivated, but let me just say, the special case is when the first L2 Betti number is also 0. Okay. So I have all of these assumptions. I mean, this setup, and I'm assuming. Well, by the way, one indication of the theorem is obvious. Okay, I already said it. Then you always get this vanishing for with the technique. So one direction is easy, and doing the other direction, this we want to produce a virtual. We want to produce anything a subgroup. So I'm going to add an extra assumption. I'm going to think about the first L2 number also being 0. And just so you have some concrete group to think about, there are other one-related groups, not just the one with Thornton, which satisfy hyperbolicity and being inversely compact special. So think about a one-related group with just 2 generators, no torsion, okay, which is hyperbolic inversely compact special. Such a one-related group is going to have the vanishing of both first and second L2 number and the correct homological dimension. Okay, so this is kind of an example. This is very a thorough example. Okay, so this is just something to keep in mind for the special case. Okay, so assume that we have the special case. What are we going to do? So the key thing is the hybrid theorem. So here, so I will give you the general case into temperature. I proved that n equals 1 base. Well, here's the theorem, and let B be a perfectly compact special group. Special here. In fact, what I need is the research condition. If you know what that is, if you remember Ian's papers, then that's really what I need. I don't care about integration. This is enough. If you don't know what is the special group, and let me be a special group, then we have the following. No, there's one thing I'm missing. Sorry.
Use the eraser, David.
There's an agent?
Yeah.
There is. Okay.
There's people that everyone has used the blackboard.
Yeah, sorry. I'm very grateful that it is very obvious. What would we be without, mentors and masters?
I mean, Martin's here, we currently, so. See mine, so we can.
Yes, that's great. So, right, we'll take some positives. The of types, sorry, I have to throw some homology types and FPN over Q. Forget about it. Okay, if you don't know what it means. So it's an idea. And now, once you have these hypotheses, then the following are equivalent. The key statements, the following are equivalent. One statement is that the L2 numbers, the ith number of the group G is 0 for every I smaller or equal to n. It's the same thing as here. And the second statement is that there exists a finite index subgroup H, finite index, D, and a map homomorphism from H onto Z, such that the kernel phi is of type FDN over Q. So there are all these homological types. So let me just remark: when n is 1, FP1 over Q is just finite generation. So okay. So if you take a virtually special or virtually reversed group, which is finitely generated, if you know that the zeros and the first L2 numbers vanish, then you virtually have a map to Z in the kernel, which is finitely generated. This is at the right side. Right? When n is 2, you get the same story, except with type FP2, which you should think about as finite representation. If you haven't seen it before, this is a homological analog of finite representation, mutability. So again, we take a group which is homologically finitely represented, almost finitely represented. If the first second L2 numbers vanish, then virtually you have a map to Z with a homologically finitely represented pair. Okay? That's what the second is. Yeah, so I proved n equals 1 version and some proved the full version. In fact, some proved it also with other coefficients. We can stick a finite fields here. It's also there's some other. It's another type of the other skill fields, right? Which you can define your numbers. Okay, so this is the big hammer that we are going to use. And maybe I'm going to keep the statement in the theorem. Yeah.
We have many theorems. There's a many applications to training approach. And you think I have one training approach with all of the first become negative. I guess all this is satisfied.
But I mean, we know that all that.
Maybe question in the high-pitched voice.
Sorry. The question is if we learn anything new about free manifolds this way, and I think the answer is no, because if you have a free manifold with boundary and it is versus private, then you know it's two-way factor, right? So what I do,
Why can I not be together on five with the non-compact surface?
Are you want to learn something about the topology back?
Yeah.
I don't know. So talk about algebra. I mean, how could I know? So you feel got that in this. No, I don't know. It's an interesting question. Sorry, I don't know.
Stefan, so sorry, I care about topology. So if you take a hyperbolic, manifold with hygienic boundaries, it's going to satisfy those hypotheses, including the L2 beta number hypothesis.
Yes.
Okay. I think that is virtually or virtually. I guess it's virtually free-by-cyclic theorem.
But I mean, we knew that. I mean, this is telling you nothing new about the algebraic side of free manifolds. That I can guarantee you.
Even with negative characteristics.
Think. Well, okay, yeah. Right.
The boundary surface we get fiber.
The boundary surface. Well, how do you mean? I mean, if it's a theoretical fiber, then just not the boundary.
Theory talks about
Yeah, I will go. Sorry. Yeah. Okay. Right. Right. What I'm saying now. So we are back in the setup. We have a hyperbolic version of a special group with these properties, and additionally, I'm requiring this, right? Why am I doing that? Because I want to satisfy the hypothesis of this theorem. So my group is virtually compact special, so it's virtually special. It is hyperbolic, so it is virtually of type F. So I get this. I can say straight away, the first thing we do, we pass to a finite index algorithm, finite index, and we want our group to be free. Okay, I don't want to do this all. The statement in the end is just about virtual properties of the group, so it doesn't have to do. So now I have a group that is of type F. It has a finite Gaussian space, so in particular, it has this homological finite property. So I'm happy with this. I have this. I have that. I have one thing of the 0 first and second delta vector number. The 0 to 1 is always 0 and it's infinite. So I have this. So then I have that. Okay. So this means that by the Pythagorean theorem, there exists an H finite index in V, and the morphism of Z such that the kernel of the morphism is type F T 2 over Q. Okay, very finite integral. Okay, so that's what we get. And what we want is we want a free kernel. Yeah. So now how are we going to massage this into a free kernel? But the point is that now the kernel. So let's observe the following thing. The homological dimension of A is now 43. This is the same as the homological dimension of Q. This is 2. And now this implies that the homological dimension of the kernel of phi is bounded above by 2 as well. Some groups can never have the higher homological dimension. Yeah? One good thing about the homological dimension. So now we know that our kernel is type 2 and it has homological dimension 2. But that implies that the kernel is of type, just homological algebra, FT over Q. Okay? It admits a finitely generated projective resolution of Q. Yeah. Okay, it doesn't really matter. So the point is that now we use an old theorem of Feldman. I think this is 1971. If my notes don't die on me, then I will know. Yeah, 1971. So Feldman proved that if you have a group of finite homological dimensions like H, and you have a map to Z, and you have a kernel, and the kernel has good enough finite properties, in particular this is XP, then the cohomological dimension of this kernel has to be strictly lower than the cohomological dimension of the group in which we say. Okay? But that tells us that the cohomological dimension of the kernel is 1. Okay, and we are done. Now starting from Swan, tell us that the kernel is 3. Okay, so this means that H is free-by-cyclic. So that means that G is virtually free-by-cyclic, and we are done with the special case. Now, but one thing that has to be said here, that's important. The kernel of phi is of type FP2, in particular is of type FP1, and I told you FP1 means finite generated. Yeah. So this kernel is not just free, it's free and finitely generated. So our group G is not just virtually free-by-cyclic, it's virtually finitely generated free-by-cyclic. So Euler characteristic of G is 0, which we actually knew because the Euler characteristic is the alternating sum of the two Bernoulli numbers. Okay, so we are done with the special case, but at this stage, it seems like there's no hope that this approach can work for the general case, because this approach gives you at the end a conclusion that is wrong. It gives you finite generated kernel. Yeah, and that is not true. Okay, I'm building the suspense here. So okay, so what do you do? Well, you make an observation. The observation is very simple, actually. The point is that subgroups of finitely generated free by Z groups are free-by-cyclic. But now I mean free-by-cyclic in the general sense. Yeah, you can easily find a subgroup here which is free-by-cyclic, but the free group is no longer finitely generated. The Euler characteristic can drop. Yeah, so subgroups of this guy are still nice, but they're not no longer restricted by the Euler characteristic. Okay, so that's it. So that's the observation. With this observation, you can finish the proof. So that I want to keep something. Okay, so now we're going to prove the general case. And we are going to reduce the general case to the special. How do we do that? Right. So the general case is exactly as written here. So now we'll prove it. Okay, so what we want to do is we want to find. Here's the game. We're going to find two subgroups A and B inside our group G. That G. Well, I'm assuming it's not complete. I have to something. Find A and B such that here's a bunch of things that we need. So, first I'm going to do some geometric properties. So G is hyperbolic, remember. So I will want A and B to be quasi-convex. And I will want them to be mononormal. I want B to be mononormal, and there's an extra condition. So B is mononormal. And I want A to intersect conjugates of B regularly. Okay. There's some geometric things. Now there's some more group theory. So I want A and B. Well, I want them to be isomorphic and free. So that's supposed to be sorry. In general case, we introduce some notation. Sorry, I want beta to stand for the first algebraic number of G. Okay. In the special case, this was 0. Now we are in the general case. Let's use that's 0. It's bigger. And what I want A and B to be, I want them both to be a copy of the free group on beta plus 1 generators. Okay. The reasons that will maybe become clear in a second. And then finally, and this is the most important thing. What we want is, well, so A and B are subgroups. So in particular, A sits inside G. And when we have a monomorphism like this, we get an induced map on first cohomology. So I'm going to go from first cohomology of G to first cohomology of A. Now, what are the coefficients? I hope Danny is listening. We put in the linear skew field here. Here we are. The linear skew field, the best skew field of them all. This is exactly the skew field we get from the Atelier conjecture. Okay. There's one skew field you should love is this one. So okay, so this is what we get. So if you have an embedding of A to G, the cohomology, I mean, these are just cocycles from G to the skew field, they restrict to A. Okay, and this is, I want this to be an isomorphism. Okay, so that's the game I'm trying to play. I'm trying to find three subgroups which satisfy all 4 bullet points. Yeah. I will not really explain how we do it. I will explain a bit, but not in full, because you probably don't care. But let me tell you some names. So the first 2 bullet points. So these 2 guys. So we are using essentially standard technology that's available. So I'm not claiming any originality in this part. So we are using results of Minasian for the convexity, and for the normality, the constructive stage, we're using Danish results, and we are using idea of Kapovic and Helankovich mapping of Weil and Rajvanseva. So that's on this bit. And now I want to tell you how we do it. Okay? Because that's what is the second bullet point? Second bullet point said that B is mononormal. Sorry. And then the section of A will conjugate to B is trivial. Yeah. Okay, how do we get there?
You feel the same thing as a division ring?
Yes, this. The skew field is the same thing as a field if you weren't indoctrinated into thinking that everything has to be abelian in your linear algebra in the class. So, right, in fact, Bourbaki calls the skew field a field, right? And for a good reason. Okay, what's the big gun? So we are going to use a beautiful theorem. So I really want to advertise this. This is by Peterson and Tom from, let me tell you, 2011. This is known as the L2 Freiheitssatz. Okay, what do they prove? So, so G is, I think, finitely generated. Yeah, let G be a finitely generated group generated by a set S. Okay, and assume that the group ring embeds in the skew field. Okay, so that's the best assumption, you see. And now, once we are in this setup, this is what the beautiful theorem will tell you. There exists a subset S prime of S such that S prime generates a subgroup 3D, generates a subgroup A 3D, and finally, so the subgroup A sits inside G, so we have a map on first cohomology of G with coefficients in the skew field. So the fact that the skew field contains the group ring turns it into a module. The multiplication is just the multiplication you get by multiplying inside D. So we have this, and we map it to the first cohomology of A with the same coefficients, and that is an isomorphism. Okay. Lo and behold, I mean, it's a fantastic theorem. It's a beautiful proof, and just 1 page long. And it tells you that whenever you have a group, this is, I mean, any finitely generated group, you can pick a subset of the generating set, which gives you a free group, and whose rank is exactly the first alphabetic number, plus 1. Okay, that's already remarkable. But it's not just that. It's not just that this group, its L2 homology is kind of similar to the L2 homology of the group you started with. The obvious map actually gives you an isomorphism. Yeah? So all the first L2 homologies witnessed by a particular free subgroup, that's extremely easy to build. You start with any finite generating set and pick a subset, and it's there. Okay. So it turns out that when we were talking with Marco, we got to this stage, we thought that's going to be very hard, but then Ismail told me about this theorem, and it's not being so hard. I also want to thank Martin, because Martin told me about this theorem a long time before that, and I forgot. So I want to stress how important this is. Okay, so this is the last ingredient, right? Because this is exactly what we want here. I want to have 2 subgroups. While finding the other subgroup is subgroup. So I want to find the subgroup A, which is a free group of the right rank and has this property on L2 homology. Okay, and then we find B using this kind of standard.
Making a quasi-convex easy as well.
It is easy because Minafian shows that if you take any finite set in a hyperbolic group and you raise every element in the set to a high enough power, it generates a quasi-convex subgroup. And this result, I did it. So I gave you in the version of Peterson Tom. We have improved it slightly. Namely, you can take this S prime and you can also pass the powers of the generators. Yeah, and this is the same proof. So that's the same problem. But yeah, so that's how you get quasi-convex is over. Okay, so now I think we have all the tools. I can tell you how the story concludes, and we are done essentially. So let me do that. Okay, now I need to erase something. Okay, I will erase the. No, I don't want to erase. Erase. Yeah, we'll do that. Okay, we'll remember what it said. Oh. So.
We can ask why you erased. So can you say what the relation is in general between this homology and the L2 variable?
Yeah, sorry, say that again, sorry.
What's the relation between this homology and L2?
Sorry, yeah, I didn't say that. Thank you. Very important point. So when so there's multiple Q fields, this one I talked about, and then inverse Q field, and it turns out that if you want to look at any L2 breaking number of a group is equal to the dimension of this module as a DG module. Okay, so when you compute homology with coefficients that are not just a module but a ring, this thing becomes a module of this thing on the other side. Okay, so when I think about DG as a left G module, then HIG DG becomes a right DG module. Okay, I'm sorry for commenting you with this, but it's true. And then once you have a module over a skew field, it's just a vector space. As I mentioned, the theory works exactly the same for fields. Okay, so it so happens in mathematical property of the skew field, all the definition of this number, if you want, that the L2 numbers are computed by homology in this group. Okay, so that's a fact. Now, also it's true that you can jump from homology to co-homology because you're doing the field. So that's why I use co-homology here. And also another important thing is that for this to be the L2 co-homology of A, I think that you can A here, there is a skew field of A. But this skew field is bigger, and when you have skew fields, obviously the bigger skew field doesn't change anything. Okay, it's all flat. The extension of one skew field by another is flat. Yeah. So 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 the point is that the DG dimension of this guy is exactly the first algebraic number of A. The DG dimension of this guy is exactly the first algebraic number of G. Yeah, and here this theorem works with any skew field as long as you have an embedding. So I can do the linear skew field, I can do also the other skew fields. Yeah, and get out of it. Yeah, we're happy about this.
So everything with this property has the same L2 betting numbers as a free group, you just have to figure out the rank of the free group.
And this is just the first algebraic number, right?
Oh yeah, this is.
Yeah, the first algebraic number is witnessed by this actually. So I would be very interested in seeing a generalization of this theorem to higher dimensions. I mean, it's not even clear what one should conjecture. Maybe there is some nice setup, some nice class of groups where you can always find the right angle dating group, which has the correct first, 7 algebraic numbers. Yeah, it will be very, but we don't know. And the reason why this theorem works is that you have an explicit way of understanding first cohomology in general. First cohomology is just, cocycles, one cocycle. So by covalently. But what I mean is that we can think of these guys as just these twisted homomorphisms from A to a field. Yeah, and that's what makes this theorem tick. Okay, I hope maybe we have some time to say something about this, whatever. So now where are we? So we are finishing the proof. Okay, this is really just the last bit of the proof. So we have our group G. That's the group we care about. Right? What we are going to do is we are going to build a group G bar by taking an HMN extension where I identify the subgroup A with the subgroup B. These are exactly the subgroups. Yeah. I found two subgroups I'm just going to identify. Why would I do this? Well, because now I get lots of nice properties. So first of all, G bar is still hyperbolic and virtually compact special. How do I know? Well, because of Hamilton Wise. This is the combination theorem, and this is exactly why I needed these two. Yeah? This is the only place where geometry comes in. So the only reason, for example, I needed hyperbolicity in the segment of the theorem is because I want to use this Hamilton-Wise combination theorem. If there was a Hamilton-Wise combination theorem which worked for compact special things without hyperbolicity, I wouldn't need hyperbolicity at all. Yeah. So my suspicion is that hyperbolicity is not important to the story in any way. But for now, we cannot consider it. Okay, so anyways, I have these two properties that's exactly what you need to get this statement. So that's one thing. What else do we need? So I'm trying to embed my G into a group which satisfies the hypothesis of the theorem and the special case. Yeah. So I want to be hyperbolic, virtually compact special. That I have. I want to have low cohomological dimensions. So the cohomological dimension of G bar is still at most 2. Okay. If you amalgamate one-dimensional thing by just a simple Meyer-Vittoris argument, see that you cannot affect anything beyond dimension 2 in homology. Okay, if you are only manipulating things in dimension 1, the dimension 2 go up by 1 by 1. So you get the cohomological dimension of 2. What else do you get? The second L2 betting number doesn't change when you do this, right? So in general, you have to compute L2 betting numbers, right? So now we compute, and again, this is just a Meyer-Vittoris argument. So when you do a Meyer-Vittoris argument to compute L2 homology, so just homology with coefficients in the skew field DG, what you see is that you have a place where you get a map from H upper 1 of G to H upper 1 of A. Okay, the map you get is not exactly this map, but it's very closely related. So there's just a little bit of massaging needed to essentially get an isomorphism. And then when you get an isomorphism in the correct place in the Meyer-Vittoris sequence, we just see that when the second L2 betting number was not affected, and that's 0 by assumption, and the first one actually ends up being the first L2 betting number of G minus the third L2 betting number of A. Okay. So this is the trick which allows you to kill the first L2 betting number, yeah, in a relatively non-violent way. You preserve lots of other problems. Okay, and now this means that G bar is in the special case. You kill the first L2 betting number. So we know that there's some H bar sitting inside here, this finite index. It maps onto Z, and it has a kernel. And if you remember, the kernel there is 3. Yeah. So now we embed into this. So we embedded the and which means that V is a subgroup, so virtually it's a subgroup of free-by-cyclic group, and then it is so. Yeah, so that's how it goes. Okay, so I still have 5 minutes, but I'm not sure if I want to. So in 5 minutes, I could give you the proof of this, but maybe you have enough. So if you want to see the proof of this, well, talk to me afterwards and happy to show it to you. And otherwise, I think
Comment. It reminds me a little bit of like so that mean I could take about virtual reality. And then at the very end, he said something about three folks with hyperbolic characteristic. And he said something like, but that one virtually that's one creation. And I think he does that stuff in quite that's a little bit like yeah, a little bit same spirit that
it's really doubling, yeah, I guess.
he does
Okay. Okay. I got
that's
it.
just a comment.
There was a question, sir.
Maybe in this situation that the compact and virtually compact pressure is involved.
Yeah. So the only reason so I want the hat bar to be reset. That's all I want. Okay. But now the question is, how do you get it to be reset? So we want a general setup in which we take a group which has your favorite properties, and I want to be able to do an natural extension. Natural extension over 3 groups where I have a lot of freedom in choosing these 3 groups. It's really a very flexible field. So if you have any setup where you know that you have taken a group, you do a natural extension over 3 groups, and you get something reset, this theorem will kick in. Yeah, because the only thing I need, the correct inspection was in the here, but it's in the but we don't have any combination theorems for reverse groups, and it turns out it's even for special groups, it's quite hard to find combination theorem unless you also implement the hyperbolic. Yeah? So the geometry is needed just here to make sure that this group in the end is reverse. That's all I want. Yeah.
There are no more questions. Let's take that again.